Imperfections in solids. Crystalline molecular state is characterized by a three-dimensional periodic arrangement of atoms or ions or molecules in space. Ideally, there should be a perfect order in this arrangement, but crystals are not perfect in nature. They do not possess perfectly ordered arrangement. This is due to impurities or dislocation of certain particles, atoms, molecules, or ions from their position. Any deviation from the perfectly ordered arrangement of atoms or ions or molecules in a crystal is called imperfection or defect. The defects may be of two types: point defects, number 1, and number 2, line defects. Point defects are basically defined as the irregularities or the deviations from the ideal arrangement around a point or an atom in a crystal, whereas line defects are defined as irregularities or deviation from the ideal arrangement in the entire row of the lattice points. In our syllabus, we will be dealing only with the point defects. Point defect can be further classified into three categories. Number 1, stoichiometric defects. Number 2, non-stoichiometric defects. And number 3, the impurity defects. Now let's start with the stoichiometric defects. If the imperfections in the crystals are such that the ratio between the cations and the anions remains the same and represented by a formula which is the same stoichiometric ratio, they are called as the stoichiometric defects. These are also called as intrinsic or thermodynamic defect. The stoichiometric defects may be classified under two heads: vacancy defects and interstitial defects. Vacancy defects. Sometimes it is observed that certain particles are missing from their lattice sites, leaving a vacant space there. This is known as the vacancy defects, which usually arises due to the absorption of heat resulting in the decrease in the density of substances as a particular ion, molecule, or atom has left the space. Interstitial defects. Interstitial defects arise when certain atoms or ions or molecules come and occupy the spaces between the lattice points of the constituent particles. These spaces are called as the interstitial sites, and these particles present in the vacancies are known as interstitials. As the number of particles in the crystal has increased, the density of the substance increases. Both vacancy and the interstitial defects are generally shown by the non-ionic solids. The ionic solids do not show these simple vacancy and interstitial defects, but they show SCHOTTKY and FRENKEL defects. SCHOTTKY defect. SCHOTTKY defect is very much similar to the vacancy defect, as in this defect, equal number of cations and anions usually go missing from their lattice points, resulting in the neutrality of that particular crystals. That is, the electrical neutrality is maintained. As the mass decreases but the volume remains the same, the presence of large number of SCHOTTKY defect sites lowers the density of the solids. The types of compounds exhibiting SCHOTTKY defects are as follows. They have high coordination number and there is a very small difference in the cations and the anions. That is, this is shown by highly ionic compounds. A few ionic compounds having this particular Schottky defect are NaCl, KCl, KBr, AgBr and CSCl. Schottky defect maintains the electrical neutrality of the crystal as equal number of cations and anions miss from their particular site. In sodium chloride, there are about 10 raised to the power 22 ions in 1 cubic centimeter of NaCl and approximately 10 to the power 6 Schottky pairs per centimeter cube at the room temperature, which means that there is imperfection in 10 to the power 16 ions per sodium chloride molecule. Next is the Frankel defect. Frankel defect. It arises when usually a small sized ion, that is, the cation, occupies the interstitial space or void in such a way that the electrical neutrality and the stoichiometry of the compound are maintained. This type of dislocation of ion is termed as Frankel defect and is also called as the dislocation defect. This defect is a combination of vacancy defect and the interstitial defect. It is a vacancy defect at the origin and interstitial defect at the new location where the ion occupies the space. Since no ion goes missing from the crystal, in the Frankel defect, the density remains the same. The Frankel defects are common in those ionic compounds which have low coordination number and there is a large difference between the sizes of the cations and anions. Frankel defects are found in silver halides due to the small size of the silver ions and in zinc sulfides due to the small size of the zinc ions. In a pure alkali halide, Frankel defects are not observed because of the reason that the ions are bigger than the voids and cannot be accommodated in the interstitial voids. Next are the impurity defects. So far we have seen that defects were created due to vacancy. But when a foreign atom occupies a crystal lattice or an interstitial space, then also defects are created. That is, they may be introduced by the addition of impurity in the ions. If the impurity ions are different valence sites from the host ions, vacancies are created. Let's see this with the help of an example. Suppose we have taken sodium chloride in a molten state along with strontium chloride. When we talk about the crystal structure of sodium chloride, when in the molten state the strontium ion replaces the sodium ions, the imperfection or the impurity is caused. As when the strontium ion, that is Sr plus 2, occupies 2 sodium plus ions are removed in order to maintain the electrical neutrality and a vacancy is created due to missing of cation. Similar is observed in CdCl2 when added with AgCl.